Mac tells me it's exactly 11 a.m., so it's time to start session 8C on WDM developments. I'm delighted that we have three great speakers this morning on the topic of DWDM developments. It's Klaus Grobe from ADVA, Shomo Roy, and Jeff Bennett from Infinera. Before I introduce Klaus, let me tell you that I'm sure you're all aware that DWDM developments continue to go quickly. So the program committee thought it was important to have yet another session on this topic to explain about the developments, to hear about these developments from vendors. So it's great that we have three vendor speakers lined up. I'd like to introduce the first speaker and make sure that we have maximum time available for the three speakers. Klaus. Klaus is a senior principal engineer in ADVA's CTO office in Munich, Germany. I know Klaus for quite some time, and I consider him one of the most knowledgeable WDM experts in the world. It's a well-known speaker in our community. This is not your first time at the TNC conference, Klaus, and this is not the first time I had the pleasure to announce you. So, without much further ado, let's hear from Klaus.
Okay. I don't know. Okay. Thanks, Eric-Jan, and thank you to the technical committee for letting me speak here again. The last 10 years, I think I spoke about several aspects of high-speed and long-haul WDM transport. This time I switched to the other end of the scale, to WDM-based access, and that means, in our case, WDM-PON, or WDM-based passive optical networking. One slide on the intended content, quick introduction, then I will say something on NG-PON2, or what is being called NG-PON2 right now, because that's the standardized version, or the most relevant standardized version of a WDM-PON. Then on some aspects of WDM-PON, like tunable lasers, the AMCC, I will explain what that is, and a quick discussion on two basic types of optical distribution networks that can be used for WDM-PON. As an introduction, there's of course a question why and where to use the WDM-PON. And that's relatively simple. The requirements for broadband access are of course increasing. That certainly refers to the access bandwidth. It may also relate to the access distances. In many networks, these tend to increase toward the range of, say, 40 to even 80 kilometers. And then there's also certain added requirements like low latency and low jitter. If you consider, may not be the most relevant thing here in the NREN context, but if you consider what's now being called front haul, that is the connection between remote antennas and their digital baseband units. That's now a new relevant trend in mobile networks. These indeed require low latency, high bandwidth, low jitter, and all of these. And then, of course, there's also the requirement for further future bandwidth scalability, and all of this leads to a single solution in broadband access, and that is WDM-PON, without an alternative. And there's only one choice. Is it a pure, what we may or may not call a pure WDM-PON, whatever that is, or is it the standardized version then being called NG-PON2, standardized in ITUT study group 15, question 2? And yes, I'm one of the standardizers. And below that, the only other relevant question is, shall we use a filtered optical distribution network that is wavelength routed, or WR, or can we use a power split one like we did with all the other PON generations, GPON, EPON, XGPON1, BPON, APON, the PON ABC, if you like. A high-level picture on applications of WDM-PON. By the way, not only in NRENS, because certainly mobile, X-Haul, front-haul, backhaul, etc. isn't necessarily a case for NRENS, but I mentioned campuses here. So a sketch that indicates how a WDM-PON may be used in a network, so it will then connect the backbone sites via a potentially passive infrastructure to the sites that are to be connected. And it can do so with services up to 10 gigabit per second per channel or per wavelength right now. And it's very likely for the near future that that can be extended, say, toward 28 gigabit per second per wavelength, maybe possibly 40 gigabit. Of course, we know we could do 100 gigabit today, but I'm referring to extremely low-cost solutions. In PON, traditionally, because PON also relates to residential access, we have much different cost expectations and much higher pressure. So with these bit rates, I'm referring to low-cost solutions. Let me have 1 or 2 slides on NG-PON2. As I said, it's being standardized. The first parts of the G989.X series are available. They can be found on the ITU web pages. They can be downloaded. There was very much debate. It started, as every useful standardization, with operators' requirements, because the operators are the customers. And the requirements initially were at least 40 gigabit accumulated capacity, at least 20 to 40 kilometers reach, legacy ODN. ODN is the optical distribution network, the fiber plant, to be supported, colorless ONUs. It was clear it would become a wavelengths multiplex-based WDM-PON, and colorless meaning that ONUs shall not have fixed wavelengths transmitters. In other words, one piece of ONU shall be able to support any wavelengths. And it was pretty quickly clear there need to be a point-to-point WDM overlay. Because it was also relatively quickly clear the main solution would be the TWDM system, time and wavelength domain multiplexed system. That means several wavelengths, each making use of burst mode time domain multiple access, like GPON, but on several wavelengths. And then there ought to be additional point-to-point wavelengths that create virtual point-to-point connections, because they are not split amongst several customers anymore. We have several bit rates for the TWDM system and for the point-to-point system. Of course, for the point-to-point system, because that ought to support all sorts of services, it is consequently all sorts of bit rates centered around 1 gigabit, 2.5 gigabit, 5 gigabit, 10 gigabit, and more in the future. There is several variants for the wavelength allocation, referred to as shared and expanded spectrum. There is, as I already mentioned, power split versus filtered optical distribution network options. And there are several reach options, like the ones here, with some really demanding numbers, because this refers to the power budget in the ODN. And the ODN is defined like this one. Like shown here, it is the fiber plant between the OLT, the optical line termination, that is the head-end equipment or the equipment in the central office, and the ONUs, that are the optical networking units or the client equipment. And that means everything that is needed in terms of filters, diplexers for directional separation, circulators, etc., what have you, is excluded from the ODN. So you can easily add another couple of dB to the required ODN power budget, and then you end up with transceiver power budget requirements in the range up to 40 dB. That is fun if they ought to be cheap. One slide on wavelength selected, that is power split ODN versus filtered ODN. Power split means there are power splitters. The obvious advantage would be they are wavelength agnostic, and that means you could get any wavelengths anywhere. It also has some disadvantages. I will comment on these later. Wavelengths routed means, well, the ODN does route wavelengths by means, for example, of AWGs, which were formerly also known as arrayed waveguide routers. That's where the name came from. The passive optics can be lumped, single stage, or cascaded in whatever way you want. There is no restriction on that, and in principle, hybrids of these are allowed. Next, why tunable lasers? I think I mentioned on the third slide that NG-PON2 made the decision colorless ONUs ought to be based on tunable lasers. Why and why only now has this decision been made? Well, relatively easy. With lasers, we can relatively easily achieve higher bit rate times passive reach products. That is higher performance. We can easily achieve 10 gigabit per second. That is well known. We can easily achieve 40 or 80 kilometers. That is well known, and we can consequently achieve the product. The only alternative to colorless transmitters are so-called seeded reflective transmitters. I will not go in any detail. Whoever is interested can talk to me afterwards to any detail you want. They are based on reflective semiconductor optical amplifiers, for example. That means these are seeded with a laser signal, and the signal is reflected and overmodulated, which, if you think about, must lead to certain negative effects because you have the same wavelengths running up and down. So you will at least have a Rayleigh crosstalk on the fiber. And several other nasty things. That's why these RSOAs, etc., do not achieve the performance, but they were certainly the earlier solutions in WDM-PON. But anyway, the decision has been made in NG-PON2 in standardization against them. And it's, by the way, really doubtful that with RSOA or similar devices I can achieve 10 gigabit or more. And that leads to the remaining problem, the problem of tunable lasers, of course. Still, cost. Why didn't we use them 10 years ago? Because the tunable laser 10 years ago would have cost a fortune. Relative easy, and nobody wants to pay fortunes in excess. One slide, and I will not go to every detail, on some contenders for tunable lasers, well-knowns and less well-knowns, if you will. Upper left, one example of a 5-section DBR laser, digital supermode distributed Bragg reflector grating laser, long name. It simply has several tuning sections which can be controlled independently, and that means it can be tuned over full band, full C band, if you will, or full L band, without directly heavily impacting what happens in the gain section. That means the launch power stays stable approximately to first approximation. As you can also see, pretty complex device. These are the things, and similar ones, of course. This refers to a special manufacturer. These are the devices you can find in tunable XFPs and tunable SFP pluses. And if you look at the cost of a tunable SFP plus, you will see this might still be too expensive. Very similar, the sampled grating Y branch laser. The name Y branch, I think, is pretty clear. Look at the right part of the whole thing. It's a competitor of the multi-section DBRs. More interesting might be tunable VCSELs, vertical cavity surface emitting lasers. Unfortunately, they have also some disadvantages, so it's not very likely. They will certainly miss the NG-PON2 requirements regarding power budget, for example. And then there are some others like fully integrated transceivers. Note these three are lasers. This is a transceiver with photodiode in polymer integration. Maybe interesting, maybe cheap. Today it seems like that a cheaper derivative of the high-end ones will win the race. Not fully decided yet. And the problem behind is, how can I make a costly laser cheaper? Well, get rid of everything you are allowed to get rid of. And that may refer to integrated wavelength lockers, because these are indeed one of the cost drivers. This may, hopefully, refer to the thermoelectric cooler. It's another piece that costs something. It may also lead to transmitters which have low power consumption. If you can get rid of the cooler, that would be great. And if you get rid of these two, you have a free-running, uncontrolled laser. Oops, we are in a problem. We can tune it, but we don't know where and how. You could reduce packaging specs, that is possibly allowed, and you could reduce optical parameters. Further things, you may reduce calibration effort. This, together with the first two, leads to a fully uncontrolled laser. We might have some problems. And the last thing that is required are high production volumes. The same thing is indicated in the sketch which came from Oclaro, which is one of the vendors of tunable lasers. Let's look at the optical parameters, which may or may not be relaxed. By the way, the problems of the tunable laser. Yeah, the problem that the vendors have is possibly the one that it may cannibalize its tunable SFP plus market. This must not happen. In order to avoid this, again, the low-cost tunable laser should be relaxed in some parameters such that it cannot cannibalize the tunable SFP plus markets. These are the possible parameters. Chromatic dispersion tolerance, yes, likely, because that would make it not useful in amplified long haul, or less useful. OSNR, optical signal noise ratio allowance, same thing, so these two are possible contenders. Line width, that might be extremely expensive, because if I relax the line width, say to 0.5 megahertz or more, it makes the respective laser completely useless for coherent. Naja, almost completely useless for coherent. That could be a very interesting thing. But then on the other hand, once you have the laser chip that gives you 100 kilohertz or so, it does 100 kilohertz. You would have to intentionally make it worse again, so it would be a new laser design. So all of this is rather complicated. And then the last two, launch power or sensitivity, absolute no-go. I show you this crazy ODN power budget requirements. You can only achieve them with highest launch power and highest sensitivity. So the opposite is true. These must be maximized. And yes, as a last remark, it's also a bit difficult to combine full band tunability and high power budget. For example, the NG-PON2 N1 class, which isn't the highest, in an SFP plus pluggable format, which has a nominal power allowance of only 1.5 watt. It's today impossible. So in fact, the early prototypes of tunable, low-cost tunable SFP pluses, and by the way, also the regular SFP pluses, the tunable ones, they are more in the range of 1.8 watt. Normally it's perfectly okay. I mean, the plug itself can stand the added 0.3 watts or so. The problem is if the cards that accommodate the cages in a system are not designed to accommodate the added heat dissipation, then the system might get into some trouble. AMCC and tuning. What is an AMCC? An AMCC is an auxiliary management and control channel. That's the name used in NG-PON2. That is an added signaling channel, added on top of the payload wavelengths, added to each wavelength. Why? Because without being told, a remote ONU cannot know where to tune. And since it is ought to tune automatically, we need means to tell it, irrespective and independent of the payload. So we cannot use in-band Ethernet, VLAN, what have you, OTN, GCC signaling. We must add something on top, otherwise the whole thing doesn't work. That's why it is standardized. The AMCC must be transparent to the payload, and hence it is added by slow baseband overmodulation on top of the payload with a small modulation index. And since it mustn't heavily impact the payload, it mustn't lead to a heavy penalty on the payload, you have to use small modulation index, and that leads to a relatively small bitrate allowance for the AMCC. De facto, it might lead to some 100 or 150 kilobit per second. which should be more than enough for signaling an OAM channel. And this is a sketch how it could be done even in a pluggable. So if it was, for example, the DS-DBR laser design, which has a SOA as a booster amplifier, you could modulate the AMCC onto the SOA section, and the payload itself would go onto the modulator of the transmitter, so the two would be independent. Works perfectly, has been demonstrated. And in the receive part, you would use a low-pass filter to extract the AMCC. And hence you have a little chip in here that terminates you the AMCC and makes it accessible, for example, via I2C. And all the abbreviations are explained here, by the way. I saw a load of slides without any explanation of any abbreviations. I try to change this. If we have an AMCC, a first very simple ONU activation procedure, again, NG.2 wording, may look like this. So this is a procedure. Obviously, I will not go into details, but the complete startup procedure of the ONU, as you can see, relies on the AMCC, whether or not it's, and that it is there. And that first, so you want to activate a remote ONU, the first thing that has to be there is the downstream, the same channel activated from the head end, because that activates the downstream signaling and tells a new ONU where to go in the spectrum. And then the AMCC, by the way, may also be used for permanent fine-tuning of the laser. So this could be the loop that is necessary if you use uncontrolled lasers, non-calibrated, without own wavelength locker. Then you tell with the ONU with a permanent loop to stay on its exact wavelength. That's how we would do it. And as a first remark, this procedure would look completely differently, much more complex, if not almost impossible to implement for constant bitrate services and in power split ODN, because you end up with all sort of interference. The ONU is not anymore allowed to start anywhere, because anywhere may be a channel where you already have payload channels. This is different in wavelengths filtered ODN. If the ONU starts in a wrong channel, it is suppressed by at least 20 dB by the multiplexer filter. So this is only a simple example just to indicate where the AMCC might come into play. And now 2 or 3 slides on wavelengths routed versus power split. There are some obvious differences. First, operational related, like support of legacy ODN, that would refer to GPON, possibly not interesting for the NREN community, because I guess the NREN community hasn't so far deployed GPON. Energy consumption, yes, there are slight differences with slight advantages for the wavelengths routed. And operations and maintenance, cost related, also similar thing. If you have to add further tunable sub-devices, this makes the whole system in the end less available, and hence you have slightly increased maintenance cost on the side of power split. And then performance related, it's relatively clear that power splitters with their higher insertion loss lead to lower reach. And then the one aspect, not mentioned here because it's mentioned on a dedicated slide, crosstalk, which leads to higher transceiver complexity for the power split variants, because they need, as I will explain, additional components. This is a high level, well, yes, it's a sketch of 2 possible implementations of a WDM-PON, OLT with a multi-channel termination here. All the PON systems, by the way, typically use or make use of single fiber working. So normally we can do the upstream and downstream on a single fiber. So it also supports areas of fiber scarcity. And then you have in the wavelengths routed a lumped filter or a cascade of filters in the ODN. And consequently you have an ONU which first separates upstream downstream, feeds the downstream onto the transceiver, on the receiver, and then you have the tunable laser section here and that's it. And if you now want or would want to use power splitting, the OLT interestingly looks identical, but since you are now broadcasting every wavelength, first the the ONU receiver needs to get a tunable filter. First problem, we don't have yet full band tunable filters. We have tunable filters that can cover 8 or 10 channels. I mean, low cost. Of course, there are in the lab tunable filters for everything you want. Possibly you need even a second tunable filter in the transmit in order to suppress crosstalk. But first I want to come to reach. The obvious, if you do the math, if you calculate the reach, this is by the way a trivial school book. The only things you need to know is the specifications given here. Then you end up with something like that, and the solid lines are wavelengths routed and the dashed lines are power split, and you can easily see that the wavelengths routed can go further. Note that this point is okay, it is power split, but it is 8 channels only. That's clear. If you only have 8 channels, you can go to higher launch power and then you achieve longer reach. But if you compare the systems for 40 or 80 channels, then always the wavelengths routed goes further. And the 3 each are without added optical amplification, then with optical amplification in the head end, and then as a third variant with optical amplification in the middle of the field. That's it for reach, so filtered gives you higher reach. 2 slides on crosstalk. Diode lasers produce side modes, indicated here. And this leads to at least 2 flavors of crosstalk, coherent and incoherent. Incoherent is the crosstalk that results from insufficiently suppressed channels, other channels, and their impact onto the victim channel under consideration. So this is the insufficiently suppressed part of the other channel that can cause crosstalk to this one, and that's the incoherent one. The coherent one is this channel here would also have side modes that are the dark blue or whatever the color is once, and some of these side modes fall into the passband of the victim channel under consideration. They cannot be suppressed by any filters anymore in this case. And that means side modes lead to severe penalties, which you can see in this diagram taken from G-sub 39 for those interested. One sketch that indeed our diode lasers do produce these side modes, and then you can also do the math and calculate, and you will find that the wavelengths routed variant has significantly less crosstalk problems. And that leads me already to the conclusion. There are several variants or possibilities for WDM-PON, including several variants of low-cost tunable lasers. They can support any bitrate you want. Of course, we could put a coherent 100 gig onto a channel of a WDM-PON. That would be no problem. It just would be not cheap, let's put it that way. For long reach, above 20 kilometers, say, wavelength routing has certain advantages, in particular systems capex, no tunable filters. Reach, possibly no reach extenders. Slightly better energy consumption. You don't have to feed the tunable filters and amplifiers, and far better crosstalk immunity. Keep in mind that in nowadays networks there is a keyword called crosstalk attack. Google it. It's an interesting thing. Crosstalk attacks happen in infrastructure, and we are talking about an infrastructure here. The wavelength routed one is much more robust against crosstalk attacks. Thank you.
Thank you very much. Thank you, Klaus. Very nicely timed. We have time for one question for Klaus. Going once, going twice. I have a quick question for you, Klaus, if there's no questions from the audience. You mentioned cost a number of times as a critical factor for especially residential areas.
Yeah.
Labor to get the fiber into the ground is an important factor of that. when you look at the overall system cost. What would be your advice for which type of fiber you should be using right now if you start with a greenfield implementation for PON?
You're mainly referring to access. Standard G652D type. Latest G652, always.
Yep, okay. So
that would almost hold for everything, with the sole exception of subsea.
Okay, understood. Once again, thank you very much for an interesting presentation. And now I'm happy to introduce our second speaker for this morning, Shomo Roy, from Infinera. Shomo is a senior manager of product marketing and strategy at Infinera. He has a broad expertise in networking, all the way from routing to optical and wireless and CDNs. And besides his full-time day job at Infinera, he is also active in teaching, and he teaches networking at the University of California at Santa Cruz.
Yeah.
Yep. Please welcome Shomo.
Thanks, Eric. Is it too loud? Okay. Thanks, Eric, for the introduction. So I'm Shomo. I work for Infinera, and as you know, Infinera is a major player in the packet optical network systems, and one of our biggest innovations is the photonic integrated circuits. So where we take multiple of the optical functions and put it on a chip, and you build the packet optical network systems around it. So using that platform, we have been able to build a very flexible layer 0 and layer 1 networks. And taking that experience in from deploying those flexible layer 0 and layer 1 network, we are going to see how a multi-layer optimized network can be built, taking some of the advantages of multi-layer SDN, which is a very hot topic nowadays. I think there is a lot of talk about SDN being used in the layer 2, layer 3 perspective, but there is a lot of play for the layer 0 and the layer 1 in order to build a really efficient, cost-effective service provider network. So I'm going to talk more about that. Hope my voice is not too loud. So this is the outline of my talk. So first I'm going to talk about some of the use cases, which is more relevant for the NRENS and for the service provider market. The second is that why really we need a multi-layer SDN, where when people are mainly talking about layer 2 or layer 3 type of SDN. And then I'm going to talk about the evolving platforms, which is more about the data plane. The first is the control plane, but then your data plane has to be intelligent enough to take advantages of the flexibility that you are building on top of on the SDN part. So I'm going to talk about the emerging platforms which are intelligent at layer 0, layer 1, and layer 2, and at each of those layers, and we are building a very converged platform. And finally, there has been a lot of talks about SDN being trial, but I'm going to talk about a deployment scenario of SDN, where it has been actually deployed and how it is actually helping the customers of the service provider networks. With that, thanks to Gian for allowing me to use this, this network, slightly blurred on the side. So you can think this is an example of a core network, and you might have the smaller networks on the side, and you are providing from the main network the services to the smaller networks. And you can think that this is an optical transport network. By optical transport network, you can think that it's a huge pool of bandwidth out there, and you can allocate those bandwidth to any of the circuits that you are going to provision from end to end, going from tier 1 sites to probably the LSC, that site. So that's the optical network, and now the things are changing. It is now becoming packet optical networks, where these optical networks are getting more aware of what is happening at the packet layer, or the layer 2 and layer 3 type of aspects. So you are looking more into the Ethernet labels, more VLAN tags and all those things, so that you can easily look at the VLAN tag and map it to a circuit that is going to be routed through this network. So still it is circuit switching or TDM that is happening, but you are having on the packet awareness on the side of the network, and you can take the advantages both of the circuit switching, the resiliency, the deterministic behavior of circuit networks. On the other hand, you are getting the benefits of statistical multiplexing by being packet aware. So now what we are talking further when we are talking multi-layer SDN is that you have the network and you have the packet part of it, which is the layer 2 and layer 3, and you got the layer 0 and layer 1, which is the main network. And then all those information, all the topology, the network information gets sent to a multi-layer SDN controller. And the multi-layer SDN controller can be talking directly to these network elements, or you can think that it can be talking to a logical layer through some REST APIs, through which it might be able to get the network information and take intelligent decisions of how to route the circuits in this network. And actually, on top of this SDN controller, and it can expose some of the APIs to, and you can build an application layer on top of it, and you can enable the APIs to be available to your customers who can write their own programmatic programs to start a circuit, end a circuit, or you can create a customer portal for them to help them build on-demand circuits for their applications. So I will just show you how the things might look like. So you have the MEF layer 2 services or the Ethernet services that might be entering the network, and it is going to multiple destinations. But it might happen that you might not need those services for a long time. You want to terminate some of the circuits and build other circuits, and by doing that, what you are essentially doing is that you are dynamically activating different services at different points of time. And what is happening is that the resources out here are now getting more efficiently shared across multiple of these circuits. So when we're getting shared in 2 dimensions, one is across all the circuits, another in respect to time, then what is happening is that the peak bandwidth requirement of the network comes down, and you can build a network with a much less number of resources. So that leads to your lower network total cost of ownership. So that's the main driver, one of the main drivers in order to build this in this concept of the multi-layer SDN. I'm going to go more details of how the network total cost of ownership plays a role with this multi-layer SDN. I think I will play just an analogy. I talked about R&E network, how one provider network is talking to multiple smaller networks. But if you take an analogy to another big tier 1 operator, they can be deploying a programmable packet optical transport layer, and it might have smaller, multiple customers. They are providing services to it, and you can actually take many of the services and you build the packet awareness in the network and map them to different bandwidth, different circuits, and all those information actually, all those control of the circuits, how the circuits should be provisioned, what should be the routing path for each of the services, they can be done by a carrier SDN controller, which has a knowledge about the packet layer as well as the layer 0 and the layer 1. I'm going to go more details, but try to start understanding why we are talking about multi-layer SDN. So you have the optical transport layer, and you have the IP MPLS network layer that sits on top of it. So traditionally, and I come from a routing background, I did my thesis on routing. When I did thesis on routing, I could never spell optical. What does that mean is that I have no knowledge of optical. What happens in the optical layer, I do my optimization at the layer 3, and I'm only interested in finding out what is my most optimized path in the layer 3. What is my next hop, and what is the next hop after that? You do all the optimization, you build your resiliency, you build your redundancy so that your layer 3 paths are most active and they are resilient. But I don't care about what is happening in the optical layer. In the same way, the optical guys, and after I moved to Infinera, I've been working on optical for the last 7 years. I'm seeing how in the optical layer you're also building a lot of redundancy, how we were building the sub 50 millisecond protection. So you are actually building redundancy at multiple layers. And what is happening is that you are actually 2 different groups are almost talking in silos, they are trying to optimize their own network. So in the end, what is happening is that you are building a network which has too much redundancy, too much excess cost involved in it. And that's where multi-layer optimization can play a significant role there. With that, let me try to also talk about like some of the traditional like network deployment. As I think taking the same thought process forward. So you have the IP/MPLS layer, and you deploy all the routers there, and you have all the packet optical transport, and where the optical transport is actually carrying those packets through the wavelengths. So traditional deployments have been that we put a lot of intelligence in the layer 3 in the IP/MPLS layer, but the optical layer is kept very dumb for most of the time. And as we are playing with our PIC, as we are building our network, we found out that with the switching, with a lot of intelligence being built in, we can do a lot of things in the optical layer. And by doing that, and another aspect of this, when you are building a network with a lot of intelligence at the layer 3 and keeping the optical very dumb. So what was happening is that the network, the total cost of the network was becoming very costly. It was becoming very costly. But if you can bring some of those intelligence back to the optical layer, actually down to the optical layer, you can actually reduce the much of the network cost. And I think next slide I'm going to talk more details how the network cost is getting reduced. But if you can bring some of those intelligence from the layer 3 on those layer 0 and the layer 1, you can actually bring down the cost of ownership of the network. But at the same time, the layer 0 that I'm talking about, or the layer 1, that needs to stay very intelligent in the sense that they have to be scalable. So as we are, as the technologies are evolving, as we are moving from 100 gig to super channels to terabit super channels, and the network has to be scalable. So even if you are bringing a lot of intelligence, at the same time it has to scale. As the bandwidth demand is growing, that network has to scale. The second is that convergence, so it has to have more intelligence, it has to understand more the packet, so understand what is the dynamics of the packet such that you can build more flexibility in the network. And the next is the automation. I think previously it used to be only dumb transport network, and nowadays we have to expose more, we have to build in more intelligence into the optical transport layer, make it more programmable such that you can control many of those optical, not the optical functions, but more or less to control the bandwidth out there in the optical network. So that's what is needed. So this kind of intelligence is out needed for this packet, for these optical networks in order to build a right kind of optimized multi-layer network. So let's look at, sorry, I drink a lot of water. So here we have talked about the same diagram we had. We have the optical layer and you have the IP/MPLS layer. Now what happens is that if we can build SDN multi-layer orchestration, if we build that kind of platform which actually have knowledge about both the layers, then those information goes out in the orchestration layer and it can decide what is the best way to route a particular service across the network. So let's look at this. So I talked about network cost, why it is becoming very high when everybody is working in silos. So IP/MPLS layer, if they are routing their packets, they are only interested in finding out the next hop for the packet, for this packet. They are not interested in how the packet is actually flowing through the optical layer. So now, as you are seeing that this packet is actually going to this destination, but it is going up to the packet layer multiple times and it is doing nothing. It is just going up and coming back and going to the optical layer. But if you have a multi-layer SDN control, then that aspect there, you have a full knowledge of the two layers of the network, and you can get the circuit, bypass all the routers, and make the service go from one endpoint to the other endpoint without having to make it go up to the routers and coming back. So what is essentially happening is that your network capex is coming down, because you are removing all these router ports which are not required. You still need the routers, but you don't need so many router ports. So you are reducing those router ports, your network capex is coming down. And the second of all, when the router ports are reduced, you are actually talking about smaller chassis. you are talking about chassis with a less number of router ports. So what essentially means that your space and your power actually comes down, and your operational expenditure also comes down. So the OpEx and the CapEx, both of which are coming down, and which essentially means lower total cost of ownership for the network. So this is the most important aspect of it, but one of the things is that in order to do that, our optical layer has to be more intelligent, it has to be more aware of what is happening in the network, and it should be able to be programmed by this SDN multi-layer orchestration layer. So let's look at, so we talked a little bit about the control plane, about how the control, how you can build some optimized circuits using the multi-layer orchestration. But let's look at some of the advancements that are being made in the layer 0 and the layer 1, and also how a layer 2 is being converged at the optical layer, and how it is getting more intelligent to address this kind of situations. I don't know what is the time left. Okay, I have good time, 15 minutes. So what we are now talking about is that how can you build a programmable packet optical networks when we see that if we bring down the intelligence to the lower layers, you can actually bring down the cost of the network. So the traditional networks have been mostly very dumb networks. They have not been programmable, they are just dumb pipes connecting two routers. So we need to go out of that and build a more intelligent networks which can be programmable, and such that you can actually control the resources from that multi-layer SDN point of view. You can control those resources, and irrespective of whatever applications you're using the network, there should not be any compromise. So let's look at how that particular optimized layer 0 and layer 2, layer 0 to layer 2 network is looking like. So here I have drawn two blocks. So this is a representation of a particular node or network element in that optical network. So the lower part, I'm calling it the photonic switching element. The upper one is more the digital switching element, where it's still doing circuit switching, but it is actually taking the optical signal and bringing it to the electrical domain and switching the electrical frames. So let's look at how this works. So this is the traditional, in traditional terms, this is the ROADMs. So you have all these colored wavelengths coming, and you want to switch them from one direction to one direction to another direction. That's happening with the photonic switching. And so you can grip this control to the SDN layer, and it says that, okay, now instead of switching this wavelength towards towards direction B, please switch it to the direction B, to direction C. So that can happen with these ROADMs, and that behavior can be controlled by the SDN. Now the next, let's look at the digital switching part of it. So when you are deploying a wavelength, you are supposed buying 100 gig worth of wavelength, you want to really fill the pipe and get the maximum return on your investment. So if you have a 100 gig wavelength and you are just sending traffic which is just worth of 20 gig, in that case you are not getting the maximum return on your investment. So in that case, what you have to do is that you have to fill the pipe fully such that the 100 gig wavelength is actually carrying the 100 gig worth of traffic, such that you are getting the most return on your investment. And that is actually provided by this digital switching layer. So you take the signal, this green light, the wavelength is coming, it is not fully utilized, so I drop it, you integrate, you add some of the other traffic that is present in this particular layer, particular node, or it is coming from some other directions. I groom them and fill the pipe nicely and send it out on this green wavelength towards another direction. So basically, what you are doing is optical switching. You are switching the wavelengths, and with the digital switching, actually you are filling the wavelengths nicely. Totally, you are increasing the utilization of those wavelengths such that you are getting the maximum return on your investment. So this is the optical and the digital switching aspect of the layer 0 and layer 1, and all these photonic, all these components are actually making the optical network much more intelligent. So you can think that you can get the ROADM layer to talk to the SDN layer to switch the wavelengths. You can make the digital switching, you can use the digital switching layer to optimize how the total bandwidth is used across multiple circuits. And I will going to show you example in the next one. So So actually, SDN is all about a lot about abstraction, like taking out all the complexity of the network and bringing a simplified view to the upper layers. So here, actually, when you are having this digital switching, you can virtualize all these optical wavelengths and think that it's actually nothing but a big pool of resources. So you can think all these slots are one small resource that is available in the entire pool. So this entire pool is nothing but the pool of resources are available in the network. So when you have to deploy, say, another 100 gig service demand, you just don't look at wavelengths. You just think that it's a whole pool of digital resources available, and use the 100 gig service demand you make this is a 10 gig service demand. The 10 gig service demand, use some of those slots, and so your total network resources now gets depleted, and the rest are available now for the rest of the circuits. So going forward, you have more services that are coming up, more services coming up, and they're just taking all of these resources. So when you are abstracting this network and sending it to the SDN layer, it is nothing but a pool of resources, and a service requirement comes in, and it looks at, oh, these are the resources available, I can route it, and what is the best way to route it, and that information you can easily do by virtualizing all this, virtualizing the network as nothing but a pool of resources. So now, once it is done, if there is now a failure, what SDN layer can do is that SDN can think, okay, what is the optimum alternate path if there is a failure? In that case, it will automatically switch and take an alternate path once there is a failure. So the higher layer can think that what is an alternate path, and it can provision it, and it can send that information down to the optical layer, and when there is a failure, you actually can switch along an alternate path. So at the interest of time, I will quickly go through some of the other concepts that are making the network more intelligent at the optical layer. So this is another concept which we have been playing a lot, which is called the instant bandwidth. So we talked about the whole pool of resources now being available, and you get a service, and you use a subset of the resources and allocate it to that particular service. But the other concept is instant bandwidth. So it comes from our super channel implementation. So every time, if you traditional deployments that you deploy 100 gig, and then you need the next 100 gig, you have to do a truck roll, you have to add a lot of equipments, you have to do a lot of planning. That increases your operational expenditure. So now we are talking about a concept for super channels, where you have already a pre-deployed big chunk of bandwidth, which is 500 gig worth of bandwidth in this example. But you don't pay for the entire chunk of bandwidth, you just pay for the bandwidth that you are required to use. So if you can think this way, I talked about in the previous slide, the big pool of resources are available, but now you think that only a subset of those resources are available, and you are just paying for that subset of resources. But now, if you think that there is a new service demand is coming, and you might be able to monetize that, you buy the next set of resources, but you don't go through the trouble of making a truck roll or adding more equipments by sending somebody out to the sites. The bandwidth is already ready. You just do a licensing scheme. SDN can enable that. So SDN can say, okay, get the license and deploy the next set of resources and make it available for the next services. So not only now that you are playing with the resources to do dynamic activation of services, but at the same time, what you are doing is that you are buying the resources as you need. So this is a very unique concept, and that comes with the super channel implementation. So as we saw here, like you buy the first one, and then as you need more, you keep on buying the next set of bandwidth as you need for your new set of services. I will talk quickly about the last level of intelligence that is happening in the optical transport network and making it a packet optical transport, where you are making it aware of what is happening in the Ethernet layer and then trying to map all these VLAN circuits into the correct ODU containers or the correct circuit. 5 minutes, okay. Sorry. So let me go back. So what is happening is that you suppose this is a packet optical platform and it is connected to a router, and there are multiple Ethernet flows that are coming to this particular platform, and these Ethernet flows might have different VLAN tags. So with the packet optical transport, you can look at the different VLAN tags and you can send them across multiple different circuits. So you are basically getting aware of what is happening in the packet layer. So you are looking at the VLAN tag or the MPLS tag, and you are sending them on the correct circuit. Another concept that is coming up is that ODU flex. So the circuit size, you can start with the bare minimum, but as your demand grows up, you can increase the size of that container, and that's called the ODU flex container. That's a new concept, and it is being used a lot. So what the SDL layer can think is that, okay, the Ethernet demand is going up. The customer can say that, can you buy me a bigger circuit? So in that case, you start with the 2.5 gig probably, and you say that, okay, can you give me the next 2.5 gig circuit? Can I buy the next circuit? So all those can happen from the customer portal, or it can be done programmatically if the APIs are exposed to the external world. So all these functions, I already talked about the digital switching. This is the photonic switching, and now this is the packet switching. And all these aspects are now integrated into the packet optical layer, and that is making the packet optical system much more intelligent as we go forward. I think I will just end the talk with one example of a deployment, and that is very important because the SDN deployments, we have been talking a lot about carrier SDN, but not much of deployments. So this is one deployment. We have worked with TACnet. So here PACnet has built a PAN SDN control layer. They integrated that with the OSS and the BSS layer. And that is very important because you are building the circuits for your customers and you want to build them accordingly. And then what we did is that this is our logical interface to our network elements, and we expose some APIs for the SDN control layer to the PAN SDN control layer. We did the integration with their software such that they can make calls to provision circuits from one point to another. And so basically what is happening is that the PAN SDN control layer, that exposes a customer console. So the customers of PACnet has a console from where they can make a request for a service, and they can specify the bandwidth, the duration, and the latency. And based on that, when that request comes in, it goes to the SDN control layer, it uses the APIs and programs the particular circuits end to end. On the other hand, it can do is, okay, yeah, I'm done, almost. On the other hand, what it can do is, here it is the customer portal. And if your customers are more into the more DevOps model where you can expose some of the APIs, what it can happen is that you can build a more programmable network, and it can look at dynamic pricing. Based on that, it can use the APIs to make more intelligent decisions on when to provision a circuit. And this is also good win-win for both of them, because the customer, they can take advantage of when the demand is low and I can activate my circuit. On the other hand, the network operator, they can reduce the peak bandwidth demand, and based on that, they can more optimally design their networks. So that's one of the good big deployments that we has happening in Asia. And this is an example of the customer portal where they can play with it to find out what is the cost of the circuit if you have to deploy it at different points of time. So this is a customer portal, but you can also do an API-based implementation where you have a programming going on, and where you can just you can make a call, find out what is the price, and make a more intelligent dynamic pricing model built into the customer premises, and you can activate your circuit as you need. So with that I will end, but there are a couple of other trials we have done, one with the Telefonica, another work we have done with the ESNet. And with that I end. So what my goal of my topic is to understand how more intelligence is coming out into the packet optical transport layer and the layer 0 to layer 2, that all these converged platforms are coming up, and that will play a big role in optimizing the network and making and keeping the cost of the network down and the total cost of ownership much lower than we have seen in the traditional networks. Thanks.
Thank you very much, Shomo.
Yeah.
We have time for one quick question for Shomo. Yes, please. Wait for the mic, please.
Thank you. It was a really nice talk. I have one question regarding the penalty for digital switching, because it is necessary to coherently receive signal and process it and transmit it again. What will be? Please, could you give us some example number? What is delay penalty for the digital switching?
You're talking about the latency?
Yeah, latency.
Yeah, I think latency, I mean, it can vary a lot depending on how much of fake and all those things you are doing, but that latency is pretty much in the microsecond level, 5, 10, 20, that's probably the range you can think of. Depends on how much you are doing in the fake layer, how much processing you are doing, and but roughly that's the number, yeah.
Okay, thank you very much.
Yeah, thanks.
Shomo told me that he has to go off-site right now to attend another meeting, and he'll be back later today. If you have questions for him, please find him after lunch. Last but not least, our last speaker for this morning session is Jeff Bennett. He's a Director of Solutions and Technology at Infinera, and he has a vast experience in data communications, working with various technologies at various high-end companies around the world. Please welcome Jeff.
Thank you, Eric-Jan. Thank you for the invitation to the committee. This presentation, it's actually a tutorial presentation that's based on a paper that was published last year. I'd like to credit my co-authors, one of which was actually Shomo. The article was in a component-focused edition of IEEE comms. What I'll be talking about here really is more of a system-level view of these parameters. And I'd like to start off really with a structure of how we've got to where we are with WDM communication, because many of us will remember the pre-coherent era. It's not that long ago. Anything before 2010 was pretty much pre-coherent, where we're using very simple modulation, direct detection with almost no signal processing at that stage. Forward error correction, of course, originally it was digital wrapper, it became forward error correction in the OTN standards. Hard decision FEC in those days, anywhere between 6.5 dB up to about 9.5 dB net coding gain. And single wavelength transponders were really the norm at that stage, and a fixed ITU grid. So in 2010, what really happened, and I'm using commercial dates here, not research and education or experiments. Commercial availability of the first coherent transmission with phase-based modulation, coherent detection, and receiver-based digital signal processing at that stage. And then later on, a couple of years after those initial coherent systems, we started to see the first generations of soft decision forward error correction. So we get a jump in net coding gain from about 9.5 dB up to probably 11.5 dB with those soft decision forward error correction algorithms. And then we get two interesting things happen later on. Probably in mid-2012, we see super channels emerging. I'll explain what those are, but basically a super channel is a parallel processing option where you put lots of wavelengths onto a single line card and you implement them all in one operational cycle. We also see last year, at the beginning of last year, the first flexible grid products emerging. And this was all about trying to maximize spectrum, maximize spectral efficiency as coherent developed. But at some point you have to say the first era of coherent has ended and we're moving on to the second era. And what we see here with the second era is more advanced phase modulation. It's beginning about now. coherent detection still, but the big difference is that we're now balancing the signal processing load between the transmitter and the receiver. That's the major difference with this second coherent era. We also get evolution, so this is not a revolution, it's not radically different, but we're getting the next generation of soft decision forward error correction with probably another dB of net coding gain. It's starting to get harder and harder to get more net coding gain from forward error correction now. And at this point, what we can say, because of the changes in the way coherent systems are being designed, is that super channels now essentially dominate and flexible grid will dominate. And the reason I'm saying this is that when you see the headline claims from vendors about how much capacity is available in the C-band, you have to use super channels and flex grid in order to achieve those headline claims. What we saw with pre-coherent, it was about 800 gig in the C-band, up to about 9.5 terabits in the C-band for the first coherent era. In the second coherent era, we see three numbers emerging. And for QPSK, you'll be seeing 12 terabits per second. For 8 QAM, it's 18 terabits per second. And for 16 QAM, it's 24 terabits per second. And the reason those three different numbers are important is there is a vastly different reach for those different modulation techniques. So, I know this, most of the talk is actually about the second coherent era. It's about advanced coherent technologies, but I just wanted to do a quick recap on the coherent receiver because it still plays an important role in the second generation. So how does a coherent detector actually work? Many of you will have used coherent detectors in the last day or two if you've tuned into your radio or TV channels, because coherent detection is used in those systems. All around us are hundreds of radio stations. And what we do with a radio receiver is we use a local oscillator. It's a local reference generator to tune into one of those channels. Now, with WDM, it's slightly different because we've already separated the received signal in a wavelength demux. But we're using a coherent detector to pick up these phase-encoded digital signals, and using that local oscillator, it becomes a very, very low noise amplifier. It means we can have a much more responsive and sensitive detector. So this is then fed into a demodulator. It's a phase demodulator where we will detect the digital signal, we'll amplify it, we're going to digitize it in an analog to digital converter, and then we compensate using a digital signal processor. So that's how coherent systems have worked since around about 2010. And they're very successful. They've really allowed us to conquer these linear impairments, things like chromatic dispersion and polarization mode dispersion. And we've reached this state where we can transmit 100 gig wavelengths over vast distances. Now, the interesting thing for solving these linear impairments, to a first approximation, you can characterize them with a transfer function that describes the chromatic dispersion, the PMD, and the transmit and receive linear impairments that are imposed on the signal. Now, this is on the right-hand side there, I'm not going to go into a lot of maths, I've only got 20 or 25 minutes here, so we're looking at a linear transfer function that describes the effects of things like chromatic dispersion and PMD. So when you compensate for those, what you do is literally reverse the effects. You implement a linear equalizer transfer function in the digital signal processor that just reverses those effects. Now, interestingly, you can almost perfectly compensate for huge amounts of chromatic dispersion and for PMD. But inevitably, as the signal propagates along a line system, which will include amplifiers, noise is going to accumulate. And if it was any other kind of system, what you would do, because of that noise, is simply turn up the power level. If we're talking about free space optics or copper-based transmission, that's exactly what you would do. The problem is, optical fiber is a non-linear medium. So when you increase the power level beyond a certain point, you find that the nonlinear component of refractive index changes with the intensity of the optical power. It will only kick in at a certain power level, the nonlinear threshold, but this is an effect that's been known for a long time. It's called the Kerr effect. I show on the right-hand side there that as the power of the pulse increases, you get this frequency shift in the signal. And again, you can model this. It's not it's not hugely difficult to model initially. You've got a linear portion of the refractive index, and you've got a second-order non-linear part of the refractive index. So these non-linear effects characterize, they manifest themselves as three distinct effects typically. Self-phase modulation happens in single wavelength systems, and you need a very high power level to encounter self-phase modulation, but what you see is the front end of pulses get compressed in this kind of situation. What's much more common is cross-phase modulation. This is in multi-wavelength systems where the channels are just too close together. And Klaus mentioned it earlier on, you get these interactions because of side lobes in optical channels. And if the symbols actually line up, the power levels line up, as I've shown there on the left-hand side there, you cross the non-linear threshold much earlier. Ideally, what you want is to get these signals not lined up. And one way you can do that actually is to have chromatic dispersion in your optical fiber, and it will help prevent this lining up of signals. There are other ways as well. Another characteristic, which is it's a really weird effect, which is you just have these two waves that interact and produce two ghost signals. And unfortunately, they produce the ghost signals at equal wavelengths equal frequencies to the spacing of the adjacent channels. And unfortunately, we operate in fixed frequency grid systems where you have equal spacing. So it's very likely that these two ghost frequencies will appear where genuine channels are using the frequencies as well. So that's called four-wave mixing. Very well characterized effects. What can we do about it? So in a coherent, in the second generation coherent systems, what we do is transfer a lot of the signal processing intelligence into the transmitter. So let's take a look at that now. Most of this diagram would be common to a first generation system, except for the addition of these two components on the bottom left, a digital signal processor and a digital to analog converter. So what you can do in the DSP is create very complex transmitter patterns that you can then impose on the modulator using the digital to analog converter. So you can see there that the DAC is driving these S1 and S2 inputs to a Mach-Zehnder transmitter, and that will allow you to model the optical pulse or the optical signal that you send into the transmitter. And there are four really important things that we can do with this kind of system. We can implement high-order modulation beyond QPSK. We can shape the pulse. We can pre-disperse the pulse for chromatic dispersion, and we can also deal with these nonlinear effects directly. So let's take a quick look at these. So higher order modulation, again, we've known about this for a long time. If we weren't talking about optical transmission, if we were talking about Wi-Fi, if we were talking about ADSL, a lot of other technologies, they're already in the 512 QAM, 1024 QAM constellations. These are well understood transmission techniques, but those are linear media. That you don't encounter the nonlinear characteristics that you do in optical fiber. The problem when we go to something like 16 QAM on the right-hand side here is you'll see the dotted line around each of these constellations effectively represents the nonlinear threshold of the power level that you can transmit that symbol. It's the same for both of these constellations, more or less. The thing is, with the left-hand constellation, you're transmitting 2 bits. On the right-hand constellation, you're transmitting 4 bits. So each bit on the right-hand side has a lot less optical power. So you end up with this concept of fewer photons per bit as you move to higher and higher order modulation. The other thing is that the resolution between the symbol states as you go to higher order modulation dramatically tightens up. If you look at the the left hand here, QPSK, you've got a full 90-degree shift required between different symbols. The resolution is actually quite lax. It's easy to figure out where these symbols are. On the right-hand side, this is only 16 QAM. It's not even 32 QAM or 64 QAM, and you've still got a very tight resolution requirement between these symbols. So the end result is that 16 QAM has about 5 times shorter reach versus QPSK, but it only delivers about 2 times increase in spectral efficiency. It's not a great trade-off. On the other hand, you might say, I don't need 4,500 kilometers reach. I could easily close links with 600 kilometers, 800 kilometers reach using 16 QAM, especially for metro systems or for systems that don't require optical protection. So 16 QAM definitely has a place, but we need to be aware that it has these limits in reach. Another thing we can do with the DSP and DAC, regardless of what modulation technique that you're using, is to intelligently shape the pulse. Now, we saw earlier that there are these side lobes onto a typical pulse that is not shaped. And the problem is, if you try to squeeze these channels too close together, you end up with the interchannel interference that Klaus talked about earlier on. If you can shape the pulse, if you could remove those side lobes, then you could squeeze them much closer together. Now, you can't simply filter them. You can't just put a hard filter and lop off the power in those pulses, because they actually contain information. What you have to do is intelligently put the energy from those side lobes into the central lobe, and that's what the DSP and DAC can do. So you can squeeze them much tighter together without a reach penalty. And the ultimate is where you can squeeze these so close together, we call it Nyquist DWDM, after Harry Nyquist, who wrote a lot of papers on digitizing analog signals. And what you can do is actually space these pulses at about the baud rate. So if you have a 32 gigabaud signal, then you could space them at just over 32 gigahertz. You'll notice I say just over, because there is in fact something called a roll-off factor called alpha, and typically the practical limit there is about 3 or 4% before you start to incur OSNR penalties. Now again, you can continue to squeeze them closer and closer together. You have concepts called super Nyquist or faster than Nyquist. Inevitably there you will have an OSNR penalty. There are things that you can do, but it just adds more and more complexity to the system. So at some point we have to take a step back and look at the fixed grid system that's been defined in G694.1 for a long time. And in fact, the first generation of 100 gigabit systems, they were spaced at 50 gigahertz spacing, and they fit very nicely into that 50 gigahertz grid. That was the limit, though. That was actually the spacing of the grid that started to become a limit. So these fixed grids were used so that individual carriers can be optically added or dropped in a ROADM. So ROADMs have to be designed using a grid. That's just the way ROADMs are designed. And you have to understand what the grid spacing is in order to be able to reliably add or drop those particular channels, let's say, from a ROADM. Well, if you're using pulse-shaped carriers, what you'll notice, this is a non-pulse-shaped carrier. If you could shape the pulses like this, you'll notice that there's a lot more space now between those carriers. And it's wasted space, because you could squeeze them a lot closer together. And if you remove the requirement to optically add or drop those carriers, you can now end up becoming limited by the fixed grid plan. So what you could do is just remove that fixed grid and have a super channel. That's what it's one definition of a super channel, is where you treat the entire set of those carriers as a single entity from the point of view of optical add drop. In other words, you don't try to optically manipulate anything within that band. You just manipulate the band as a whole. And what you do is you put guard bands at the ends of the super channel so that the ROADMs can optically add and drop that particular band of wavelengths. So that example shows a 12 carrier super channel, and you might say, well, Infinera is famous for its photonic integrated circuits. Does that mean we implement it all on one chip? This is in fact our next generation system, but you don't have to take the whole thing as one super channel. It can be flexible. It's not totally flexible, because you still need to manage the optical spectrum. I'm going to talk about how G694.1 has been adapted to cope with that. But what we can also do is create something called sliceable superchannels, which is where if you start on the same line card with all of the carriers, you can actually retune some of those carriers so that you create guard bands within what was the super channel, and now you can optically add and drop those those superchannels. So each one of these becomes its own superchannel, but it may be on the same chip, the same line card. The problem when you do that is that you start to lose spectral efficiency, because if you have everything as one superchannel, this 1.2 terabit superchannel, I say here it's 462.5 gigahertz. That's the total width of that superchannel. It's QPSK modulated. If I decided to split this up so that I could optically add or drop, let's say, 4 different 400 gigabit Ethernet services, I would end up putting in some guard bands. And the total width there is 487.5 compared with 462.5 for the non-guard band system. And if you go to the logical extreme of taking each one as an individual 100 gig carrier, you end up going back to basically a 50 gigahertz fixed grid. So the more that you slice, the less spectrally efficient this becomes. Now remember earlier on, I said that really second generation, or the second coherent era, is going to be dominated by superchannels. This is what I mean. I mean that you treat the entire C-band as one superchannel. So in other words, you don't try to optically add or drop the entire C-band. So how do you manipulate that capacity? We're talking about 24 terabits. We don't have too many 24 terabit clients. So how do you groom services into that? OTN. You have a non-blocking OTN switch. You feed the entire 24-bit superchannel, 24 terabit superchannel into an OTN switch, and you can manipulate that with full spectral efficiency. That's one way to do it. Now, obviously, you will fit along the spectrum here. Very few people will have the entire C-band as one superchannel. At the opposite extreme, hopefully very few people will want to go back to a 50 gigahertz split so that you can fully optically add drop these systems. You're going to be somewhere in between. Unfortunately, it's completely flexible as to where you go across that spectrum. So just a word about the way that G694.1 has evolved. The latest editions of this include a flexible grid. And the way you define a flexible grid is that the flexible slots themselves have a granularity of 12.5 gigahertz, but the center frequency of that flexible slot has a granularity of 6.25 gigahertz, half of the potential slot width. You have an anchor frequency. It's the same one that we've always used. It's 193.1 terahertz. And all of the flexible slots are defined with respect to that anchor frequency. And that's outlined there in red. So you can actually define any flexible slot. I've actually taken this from the standard document. I'm not trying to create my own, because they're quite complicated to define. Any slot is defined by 2 numbers, N and M. So the center of a given flexible slot is N times 6.25 gigahertz from the reference frequency. If N is a positive number, it's towards the higher frequency end. If N is a negative number, it's towards a lower frequency end. And it's M times 12.5 gigahertz in total width. Now it sounds complicated, but we get computers to do these things, and apparently they're very good at that. So the interesting thing about flexible grid, as I said, superchannels become mandatory, because to achieve the fiber efficiency claims, the capacity claims in next generation coherent systems, you have to use superchannels. This is a superchannel, by the way, and it doesn't matter whether it's based on one line card or many line cards. We've seen demonstrations by people who basically just take ordinary 100 gigabit transponders and they tune them so that they're at a Nyquist WDM. That can be called a superchannel. What we like to think of is that a superchannel should be based on a single line card, because that's the way that you achieve operational scale. It doesn't matter whether it's based on photonic integrated circuits or discrete optical components. You could have a single line card with lots of optical circuits on it, or with discrete components. Now, it would be very expensive to do that, but you could potentially do it. We prefer the approach based on photonic integrated circuits. Another function we have in the DSP and DAC is to predisperse a signal. Now, why would you want to do that? Well, we know that a signal will be dispersed as it travels along the fiber. This is chromatic dispersion. So these are not separate pulses. These are the different wavelength elements of the same optical pulse. And so it becomes more and more difficult for the receiver to determine if this is a 1 or a 0, because the pulse becomes very dispersed. I've mentioned that in coherent systems, we can completely compensate for chromatic dispersion in the receiver. So why would we want to change anything? Why would we want to pre-disperse an optical pulse? Because what you could potentially do is disperse it in the negative direction before it travels down the fiber. A couple of different examples I'll give to you. Modern submarine cables, I think this is what Klaus was referring to earlier on. He said you should use G652 fiber everywhere except for submarine. Well, now people are deploying G654, large area fibers, with complete positive dispersion all the way along the fiber. And they're doing this because they can, because now you can pre-disperse in the receiver, in the transmitter before you insert the signal into the fiber, and then deal with the rest of the dispersion in the receiver. So you're kind of splitting the load between the transmitter and the receiver in order to deal with chromatic dispersion. So you could have it all arrive with zero dispersion. You probably won't do that, but you could do if you wanted to. That's one example. Another example, G653 fiber, right? We know that G653 is a nightmare fiber for WDM. It has zero chromatic dispersion in the C-band. It's difficult to use WDM with G653. If you could pre-disperse the signal before you launch into G653, you could now use it as a high-capacity WDM fiber. So nonlinear compensation is I think the last thing I'm going to look at in the DSP and DAC. I'm not going to go into details. There's lots of algorithms now that, in general, they're expecting to deliver about 1 dB of OSNR improvement. Lots of different algorithms. These are very complex algorithms. And commercial deployments are going to appear over the next few years, but let me just very briefly show you why they are complicated. This is the nonlinear Schrödinger equation, or a representation. It's a non-trivial exercise to compute these things in real time at speeds of 100 gigabits per second. So each equation is essentially representing a kind of complex envelope of these two orthogonally polarized components of the electric field. What we're seeing here this is orders of magnitude more complex to solve than linear compensation, but it's starting to happen. Digital backpropagation is a big technique that a lot of people are talking about. If you look at it today, it's almost always done either with one wavelength, which is achievable in ASICs, or when you do a multi-wavelength approach, it's always done with offline processing. So, to process 1 second's worth of impairments, it takes you 5 hours, right? It's a very intensive calculation. So the end result of this, all of these different characteristics, transmitter-based pulse shaping is going to increase the spectral efficiency and the capacity on the fiber from about 9.5 terabits to 12 terabits using QPSK. 8QAM is going to deliver 18 terabits, 16QAM, 24 terabits. All of those are assuming the entire C-band is one big superchannel. Dispersion management, very applicable on submarine links, but it's basically enabling a 5 times increase in chromatic dispersion compensation. The next generation of forward error correction is getting more and more difficult to achieve net coding gains. It's saturating out at about 12 dB. And then nonlinear compensation, we're expecting another 1 dB roughly of OSNR improvement from these techniques. So what I've talked about here, I've outlined 3 distinct areas in the evolution of optical transmission: the pre-coherent, the first coherent era, excuse me, and the second coherent era. We're in transition at the moment to the second coherent era. I can't finish. I'm sorry. Oh dear. And flexible grid and superchannels are becoming mandatory because of the way that this second coherent era is evolving. Just about managed to finish before my voice died. Thank you very much.
Thank you very much, Jeff, for a very interesting tutorial on second generation coherent. I hope your voice will last for one more question from the audience. I guess everybody wants to go to lunch, but I won't let you go yet. I have a quick question for you. I spoke with a photonic engineer once, a couple of years back, and he said to me, never underestimate the power of silicium, meaning that you can add a lot of processing power to next generation optical.
Yes.
But you just said there's a lot of processing involved. would you say that the processing involved in second generation coherent is the limiting factor at this moment in time in the developments?
It pretty much is, and I'll tell you why. All of us have probably experienced this firsthand. In this, I'm just looking, this laptop has a Core i5 processor. What you will have noticed is that CPU speeds, clock speeds, over the last 10 years or so, don't really seem to be getting faster. And that's because individual serial processing rates in silicon have leveled off. It's a big problem. So what does Intel, what does AMD do? They give us multiple cores, right? On a Core i7, you've got 4 physical cores, you might have 6 or 8 physical cores. On graphics processors, you've got 1,024 cores on a high-end graphics chip. So the same thing is true in optical electronics, optoelectronics. The serial processing rate has kind of tailed off. We had 2.5 years ago 32 gigabaud optoelectronics. Today, really leading edge is 44 gigabaud, almost hasn't increased. So what we have to look for are techniques to go parallel. So super channels are a way of going parallel, but we've already explored polarization multiplexing. That's kind of parallel, it's 2 parallel channels. And QAM, these QAM techniques are parallel because they produce parallel outputs that you send into the DSP. The more you can do that, the more you can spread the parallel load, the better. And there are other techniques that I can talk about probably at next Terina.
At tnc15, yes.
Exactly,
Thank you
yeah.
very much.
Okay.
I would like to thank all 3 speakers. Right. That means it's lunchtime. A few quick announcements. My voice is doing the same. Please have a look at the posters. They're quite interesting this year. In the afternoon, during the coffee break, the presenters will be there and able to explain to you. Look at the demonstrations. They're also quite interesting. And we value your feedback. Through the website of tnc15 homepage, there's a button at the right-hand corner. Please click that. Give your feedback on the sessions. We love to improve the program further for next year. And last but not least, the gala dinner tonight. Please be aware that the buses will leave at 7:15 here from the back place where the opening reception was of the conference center. And the good news is tomorrow morning we'll start 30 minutes later for you to enjoy dinner better tonight. Thank you. Have a good lunch.